Okay, so one thing I'd like to stress about the above derivation, you can see that we didn't use anything special at all about the metric. And a consequence of this is that scaling symmetry is a very general symmetry that's present in conformal field theories defined on any manifold. So whenever you have a conformal field theory, it will come with a scaling symmetry. Now notice that scaling is not a symmetry of ordinary CFT. So scaling is not a symmetry of ordinary QFT. Now, one of the things that's interesting to explore when you have a symmetry are what are the physical consequences of the symmetry. So let's just remind ourselves when we learned that quantum field theories were Poincare invariant, there were a few things that we knew. So the first thing was physics was the same, physics is the same in all inertial frames. Okay, so what did that mean? Well, if you've got a collection of charges that are at rest in some frame, you know that the equation that will describe those charges is Maxwell's equations. If you now boost that frame up to some constant velocity v, now those charges are moving. They are setting up a current. So you've got charged particles now moving in the presence of currents. So you'll have both electric and magnetic fields. But we know, because physics is Poincare invariant, that Maxwell's equation still governs that system of particles. Also, from the form of the Lorentz transformations, we know the speed of light is a constant, meaning any inertial observer measuring the speed of light will always measure the same value. We also know that no information can travel faster than the speed of light. So that comes from Lorentz invariance. As far as translations go, we also learned a lot of interesting things. Because of translations, we know that the laws of the physics are the same everywhere. So the laws of physics in London will be exactly the same as the laws of physics in Huzhou. We also know that the laws of physics yesterday are the same as the laws of physics tomorrow. And that's because of time translation invariance. And all of these invariances come with conservation laws. So the fact that we've got time translation invariance tells us that energy is conserved. The fact that we've got space translation invariance tells us momentum is conserved. The fact that we've got rotational invariance tells us that angular momentum is conserved. So symmetries and conservation laws are very, very important ideas. And one of the questions that we're going to be asking in a lot of detail is what are the consequences of conformal invariance? So if you tell me you've got a theory that's conformally invariant, then what are the consequences of saying you've got conformal invariance? Well, we're not going to give this answer. Well, it'll take us a little while to give a complete answer. So we're going to start answering it bit by bit. So here's a first pass at this question. Let's imagine that we start off and let's look at physics at a scale of 10 to the minus 10 meters. So if you're at 10 to the minus 10 meters, what kind of physics are you talking about? You're talking about atomic physics, okay? 10 to the minus 10 meters, that's roughly the size of an atom. So if you want to think about something specific that you could be thinking about, you might be thinking about a hydrogen atom. And if you want to know what is the laws of physics that you would use to describe this hydrogen atom, well, that's easy. You know, you would be using something like the Schrödinger equation. Okay, so this would be your description. Now, what we could do is, if nature was really scale invariant, we could perform a scale transformation let's perform a scale transformation with the parameter lambda, which is 10 to the power of 10. And performing this scale oh, that doesn't look good. Performing this scale transformation of lambda is 10 to the 10, we would land up with a length scale of 1 meter. And if you ask what physics are you talking about now, well, now you're talking about classical mechanics. What law would you use? Well, you'd use Newton's mechanics. So let me just write F is equal to ma. That would be the physics. What's an object that you could be studying? Well, maybe you're studying a tennis ball, or maybe you're studying a beach ball, something like that. If scale invariance really was a symmetry of nature, we should be able to zoom in and zoom out, and the laws of physics would remain unchanged. But here we've zoomed in, we've given an enormous magnification, and we know very well that the physics of the Schrödinger equation, the physics predicted by quantum mechanics, is very, very different to the physics predicted by Newton's law, classical mechanics. So that means that, in fact, conformal symmetry and scaling symmetry that we're talking about here is not a symmetry of nature. Now, if it's not a symmetry of nature, you might wonder, why are we studying conformal field theories? What is their use? And answering that question is going to be one of the questions that this set of lectures will answer. So we'll get there. It'll take a while to answer that. For now, I want to start asking a slightly different question, but aimed at figuring out why are conformal field theories still useful in our description of nature. And the question I want to ask is, how special are conformal field theories? Now, how special are conformal field theories? Now, this is not a great question as it's posed. It's a bit too vague. So let's try to tighten it a little bit. Let's say, given a quantum field theory, so given just a general quantum field theory, how carefully do we need to tune its parameters to get a conformal field theory? So if I just give you some general QFT, how carefully do we need to tune its parameters to get a conformal field theory? And this is a much better question than asking how special are conformal field theories, but it's getting at exactly the same thing. Okay, we'll continue in a moment.